Hello, this is the Further Math Support Programme in Wales, talking you through a solution to question 18b on the June 2018 Higher Non-Calculator GCSE paper. The question is on the topic of graph transformations. Okay, so here we go. Here's the question. Use the following axes to sketch the graph of y equals 2 cos x for the values of x from 0 degrees to 360. You must indicate any important points on both axes. So what's the thinking here? Well, first up, this is a question about sketching 2 cos x, so we need to know what y equals cos x looks like. Now the good news is that in the very first part of the question they actually gave us a sketch of y equals cos x, so we can use that. Secondly, something I find quite handy is to think about what happens at particular values of x, so we'll see that in the next slide. The range they've asked us for is 0 degrees to 360 degrees, which matches the axes they've given us as well. That's good. And then finally, what does this phrase important points mean? Well, typically when sketching graphs, important points means places where it crosses the axes, maxima and minima. But in particular, in these trig graphs, the important thing to indicate are the amplitudes on the y-axis, and if the graph has shifted along, then we need to show the new crossing points on the x-axis. Okay, so here at the top we've got a picture of the graph of y equals cos x. We're going to think about what happens there, and at the bottom we've got the axes on which we're going to actually draw y equals 2 cos x. So, as I said, I quite like thinking about what happens at particular points. You may have other ways to do it. You can obviously stick with that. But if we think about x equals 0, cos of 0 is 1, so 2 cos of 0 is going to be 2. 90, cos of 90 is 0, so 2 cos of 90 is twice 0 is 0. And similarly, we've got 180. That's minus 1. If we double that, that takes us to minus 2. 270, cos of 270 is 0. If we double it, it's still 0. 360, cos of 360 is 1. If we double that, it will take us to 2. And that line of reasoning works for any x value on the graph. If we think of this one here, with the point is at the y value of the point is that of cos x, so if we do 2 cos x, it's just going to double the y value up there. And we can transfer our thinking, those points, down to the lower set of axes here. Now, what we need to do is mark the important amplitude on the left hand side. So if I've marked a 2 and a minus 2, it's not sufficient to know what we're doing. We've got to show the examiner we know what we're doing as well. So we've shown that the amplitude has doubled, and then we need to draw a smooth curve through our points. We mustn't join up these dots with straight lines, otherwise we won't get the mark. So if we do that, we get something looking like this. Now, you didn't have to do all those points. You could just check that you've got the idea that 2 cos x is going to stretch the amplitude. Perhaps you might want to check with just 1 point. Once you've got the idea, then you can actually draw the curve straight from cos x. You're just going to double the amplitude and do that. So that's also an equally good way of doing it. Okay, so here we've got the next part of the question. It says use the following axes to sketch the graph of y equals cos x minus 1 for values of x from 0 degrees to 360 degrees. You must indicate any important points on both axes. Well, what's our thinking? Well, our thinking is very much the same as the previous case. We still need to know what cos x is like, because our graph relates to that. Handy to think about particular values of x, or that's certainly one way to do it, one way I quite like doing. Ranges again 0 to 360, which is what they've given us on the plot, so that's great. And important points are what they were last time. Okay, so let's have a look at that. This is the same setup as before. So at the top, we've got a graph of y equals cos x. We're going to think about what happens when we do cos x minus 1. Then we're going to transfer our thinking to the graph below so we can sketch the graph of y equals cos x minus 1. So again, we can choose particular points and see what happens. So if we think of the point where x is 0, cos x is 1, if we do y equals cos x minus 1, we're just going to subtract 1 off that y value. Similarly, at x equals 90, we're going to subtract 1 off the y value, and this is going to work for all points on the curve. We're just subtracting 1 from the y value and shifting it down. So I'm going to shift my points down just to transfer my thinking. But if you'd got the idea that minus 1 at the end is shifting it down, then you can just draw the shifted down version. So here we go. Important, or as they say, mark the important points on the y-axis. We need to show that the amplitude, well, the amplitude is unchanged, but we've shifted it down, so the minimum is now at -2, and the center line is now at -1, and the maximum is at 0. Again, we need to join those points with a smooth cos x-like curve, except it's been shifted down. So there we go. And there we go. Job done. Job's a good one. So we're going to vary the question now. Now this is from a part of the syllabus called graph transformations, and there's actually 4 different kinds of transformations they look at. So we've looked at, if you've got a function, we had cos x, we've looked at doubling that, and we've looked at adding something to it. What you can do instead, the 2 alternatives, is instead we could multiply the x argument before we apply our function to it, or we could add or subtract something to the x argument. So those are the 4. So I've varied it by, this time I'm going to multiply the x argument. I've changed the function to sine. So this part of the syllabus, we don't have to use trig functions, but I've stayed within the trig world and used sine. I've stuck with 0 to 360. So our thinking to do it is going to be very similar. We need to know what y equals sine x looks like this time, because we're doing sine 2x. As I said, I find it handy to think about what happens to particular values of x rather than memorize all the 4 possibilities. But you need to work with what works for you. I've stuck with the range and important points. Again, we still need to communicate to the examiner that we know what we're doing, and we can see what's happened to the amplitude and things like that. Okay, so same setup as before. We're going to do a bit of thinking on the top set of axes, and then we're going to actually sketch the function y equals sine 2x on the bottom set of axes. So what does y equals sine x look like? Well, it looks something like that. Sine wave, period 360, amplitude 1, so varies between -1 and +1. Now, as I say, I quite like thinking about what happens to particular points. So if we think about the point 90, or rather the x value 90, if we're going to draw y equals sine 2x, then we're going to have to double that. We're going to have to find the value of sine 180. So we're going to have to draw this value of sine 180, except we're going to draw it in the 90 position. So this graph is going to be compressed by a factor of 2. So we're going to pull that back, the blue point back, and draw it in the position of where we've got 90 there. So let's consider a different point. If we consider 45, then again, instead of drawing sine of 45, we're going to draw sine of twice 45. We're going to draw sine of 90 at this x value. So we're going to draw this point on the curve here, except we're going to pull it all the way back there, and that's where we're going to draw it. So the curve looks like it's been squashed by a factor of 2. So if we draw that, we'll see it's going up and down, and when it used to take 360 to do a whole period, we've now got a period of 180. Amplitude is unchanged. There we go. Done it. Well done us. Well, a bit of bonus material now. Something which sometimes is tricky to remember is which curve is which. So people know that the sine and cosine curves go up and down that way, but they're not always sure, does it start at 0 or does it start at 1? Well, the good news is you don't have to commit everything like that to memory. If you've managed to get your head round SOHCAHTOA, you can easily just work it out. So if we think that sine x in SOHCAHTOA world is opposite over the hypotenuse, and we just think what would happen at a very small angle? Well, the opposite would be very, very small and much, much smaller than the hypotenuse. So the opposite over the hypotenuse, the value of sine x, would be close to 0. So it's got to be this top graph here, which is the sine graph. Similarly, for a very small angle, we can see that the adjacent and hypotenuse are very close to the same size. The hypotenuse is slightly longer, but again, we can see their ratio is close to 1. So for a small angle, it's got to be close to 1, so that's got to be the cosine graph. So we have just seen a solution to question 18b on the June 2018 higher non-calculator paper, and the topic was graph transformation.